Welcome, my dear students. This next class, in the last class, we discussed about the take a two composition of a two linear transformations. We prove a composition of S T inverse is the same as a T inverse and S inverse, and also we show that the composition of S T is 1 1 is isomorphic, then T is 1 1 and S is on 2, and also we have to show that whenever dimension of a all the vector spaces are the same, then composition of these two transformation is an isomorphism, then T is an isomorphism and S is also isomorphism. So now in this class we discuss some problems on the related to the composition of a linear transformations. Okay, so let's start with the one problem, and this problem we just say that we take a S RST we have to define as a three different transformations. In the form of a R of E1 is defined is this form. R of E2 we have defined E1, where E1, E2, En are the standard basis. So we have E1, E2 and E3 are standard basis, and you know that E1 is a standard basis for R3 is the element of the time of a 0 1 0 0. E2 is the form of a 0 1 0, and we have a E3 is the form of a 0 0 1. Now because I will define R into this form, and similarly define S in the standard basis form, and T is also defined into the standard fashion. Now the question is this: find the range, kernel, rank, nullity of the following linear maps RS, RT and RST. Okay, so we try to find all these linear maps one by one. First, what we should try, first we write the general linear transformation of this R. For writing the general linear transformation of R, we have to assuming that any values for, we take a x, y and z, any arbitrary element into the R to the power 3, then this x, y, z, you know that any arbitrary element can be written in the form of a linear combination of the elements of the basis. So we just say that we take a alpha times of a E1, alpha 1 plus alpha 2 times of a E2 plus alpha time 3 times of a E3, and now because E1, E2, E3 are the standard basis, so we simplify this. By this we getting alpha 1 is equal to x, so alpha 2 is equal to, you have a y, alpha 3 is equal to z. So we can say that we just we can write this standard basis in the form of this. So we just take in the form of this, we take this means we can say that x, y, z can be written in the form of x times of E1 plus y times of E2 plus z times of E3. Now operating T into this for operator is equal to R. So R of x, y, z can be written as x times by the R is a linear map. So we can write use the linearity condition x R E1 and then v y of R of E2 plus z R E3. Now we know that R1 is we define as a E1 plus E2. Here you can just see that R1 is a E1 plus E2, R2 is a E1 minus E2 plus E3, and this 3 E1 plus 4 E3. So just take a so this means we can just write into the form. So this means x R is defined as is the form of a E1 plus E2. So we just say that this is nothing but is equal to E2, and plus y time R of E2 is defined in the form of a E1 minus E2 plus E3, and now we have to define the R3 z times of a 2 E1 plus 4 times of a E3. So this is 4 E1 plus sorry 3 E1 plus 4 sorry this is a 3 E1 plus 4 E3. Okay, now this can be written as a coefficient of this E1 here, E1 here, E1 here. So we can say that x plus y plus 3z, and now we have a x minus y, this is simply is equal to E2, then E3 is equal to y plus 4 times of a z. So, R of x, y, z we can define in the form of a general form of a this the linear transformation in the form of a x plus y plus 3z, x minus y, and then we have a x we have a y plus 4z is there. Similar fashion we can write the t because t of x, y, z can be written as a, again similar fashion we can write x times t of E1 because this respect to the standard basis, we have a y times t of E2 plus z times t of E3. Then we have to substitute the value for t of E1. T of E1 is equal to, you have a E1 minus E2 plus E3. So, this means E1 minus E2 plus E3 plus t of E2 is equal to 3 E1 minus 5 E2. So, you have a y times 3 E2 minus 5 times E3, 3 E1 minus 5 times of E2. So, this is 3 times E1, 5 times of E2, and plus z. T of E3 is defined the 3 E1 minus 2 E3. So, this we can say this is a 3 E1 minus 2 times of a E3. Now, we can just say that this is written in the form a E1 coefficient is equal to this. So, we have a x plus 3y plus 3z, and then we have a y is equal to, you have a minus ka x, and E2 is equal to minus ka 5y, and then you have a simply is equal to minus ka 2z. So, t is defined into the form of a, we have to just say that in the form of a this sorry, this is we have to just in the form of a, so we just see this is equal to E1 5 E1 plus 3 E1, and then you have a 3 E1 minus 5 E2. So, this is equal to, you have a so this means x E3 is equal to, you have a, sorry, this is equal to x, and then you have a simply is equal to, you have a x, and then you have a E2, then you have a minus ka 2 times of a z. So, this is equal to, you have a t. Now, similar fashion we can define as s of x, y, z, and then x of y, z can be written in the form of x times of a s times of a E1 plus y times s E2 plus z s of E3 x. S E1 is equal to, you have a, just check S E1 minus E2. So, we have to just say that E1 minus E2, and then plus y S of E2 is equal to, you have a E2. So, we just say that E2 plus z times E3 is equal to E1 plus E2 minus 7 E3. So, E1 plus E2 minus 7 E3, and this can be written in the form of x and plus z, and you have a minus x plus y plus z, and then you have a minus ka 7 z. So, this is s x y z we have to define into the this form, and t of x y z we define into the this form. So, now we have to try to find the value for R s, R composition S. So, we have to just say that R times of a S of x y z, then R times of a x y z is equal to this. So, this is, suppose this is, you have a x1, this is you have a x2, this is you have a x3, and then we can just say that this is nothing but is equal to R times of a, you have a x plus z minus x plus y plus z, and then you have a minus ka 7 z. Now, operating R is equal to what? X plus y plus 3z. So, x you have a x plus z, and then plus y. So, you have a minus x plus y plus z, and then sorry, this is okay, this is clear. Now, we have a plus 3 times you have a 3 times minus ka 7 z, and then next term is you have a x minus y. So x plus y minus ka minus plus x minus y minus z, and then this is the second term. Now we have a y plus so minus x plus y plus you have a z, and you have a minus ka 4 times of plus ka 4 times of a minus 7 into z. So this means we can say that our this composition can be written in the form of this x is cancel out. You have a now you have a y and then you have a 21, and then you have a 2 24 23. So plus this is minus ka z 7 21, and then we can just substitute. This is equal to you have a z, and this is a 2z. So this is plus ka 19 z, and then you have a y is cancel out here. Then you have a 2x minus z, and then you have a here you have a minus x, and then plus ka y, and then you have a z and 28, and this is minus ka 27 z. So our composition S is equal to we have a like this y plus this should be a minus, sorry, this is a because this should be a minus times because of this minus 21 and substitute minus 2, so y minus 19 z. Then we have a 2x minus this is here, this is 2x minus z, and then you have a minus x plus y minus ka you have a we can say that 27 27 or just you just 7 4 28 27 z is there. Okay, so now we just take into this form. So now we just find what is the rank and kernel of a this map. So we just try to the kernel of this we can take R composition of RS of this x y z is equal to 0. So just we write is this RS composition. So RS of x y z is equal to you have a clearly this y minus 19z. So y minus 19z comma you have a 2x minus z, you have a 2x minus z, and then we have a we take this minus x plus y. So this is a minus x plus y minus 27z. Now we just try to find the kernel of this, means we find the kernel of R of S, means we can show that finding the kernel of this we can show that R of S x y z is equal to 0. So this implies that we can say that y minus 19z is equal to 0. Now 2x minus z is equal to 0. Now minus x plus y minus 27 z is equal to 0. So from here we can say that z is equal to you have a 2x, and then you have a y is equal to you have a y is equal to you have a 19z. So we have to substitute the value for y and z y z, then we can say that is equal to 19 into 2x. So this is equal to minus x plus you have a y is equal to 19 into 2 38x, and then minus ka you have a 54 x is equal to 0. This implies that you have x is equal to 0. And now if x is equal to 0 implies that z is equal to 0. If z is equal to 0 implies that y is equal to 0. So ultimately what we get the kernel of R and S is equal to you have a 0. So we can say that the dimension of kernel of RS is equal to 0, and then we can say that the null space of this is equal to, so nullity is equal to 0. So we can say that dimension of this, so nullity is equal to, you can say that of a R and S is equal to 0. Now next what we find that what is the So that we can just dimension of this is equal to 0. So nullity is equal to 0, and then this is the elements of this kernel of S we have to finding this. Okay, now I will try to find what is the range of this. So we can just write this R of sorry, we just say the range. So R a range of, you just take a here, so okay, range of composition of RS. So we just write in the form of this. Is the form of like this. You have a y minus 19z, then you have a 2x minus z minus x plus y minus 27z. This can be written in the form of a span of, you have a x, if we take right in this, we can write this is a span of, we have a x times, you have a 0 and 2 and minus 1 plus y times is equal to 1, you have a 0 and you have a 1 plus z times you have a minus 19 comma minus 1 minus 27. And now just clearly we say that these three vectors are, so we can say that span of 0 to minus 1 and we have a 1 0 1, and then we have a minus 19 minus 1 minus 27. And now clearly these three vectors are linearly independent. So these three vectors are linearly independent, means we can say that range of RS is nothing but is equal to complete R3. So we can say that dimension of range of RS is equal to, we have a 3. So this implies that we can say that rank of this RS is equal to 3. So rank is equal to 3, nullity is equal to 0. And now if you want, we can verify this by the rank nullity theorem. Rank nullity theorem is say that the dimension of R3 can be written as a dimension of kernel of RS plus dimension of range of image of RS. Then this is equal to, we kernel of RS we take calculated 0, and this is we calculating 3, and this is equal to 3. This is verifies the theorem of also. Okay, so this this we just say that we have to calculating this the first part of this this question. RS is equal to we have a this, so we should find that the range of RS and kernel is also the range is equal to R3, kernel is equal to 0, rank is equal to, you have a 3, and nullity is equal to, you have a 0. In the similar fashion we can calculate R and T, and then similar fashion we can calculate the RS T. We take a operation into this. So we have already calculating this. So I just leave the other two parts as a home assignment for you. You try to find the what is the range of RT kernel and rank nullity of this RT, and similar fashion you can calculate, because I already calculate the general formulas for R, S and T. We have a R, S and T, general formula is R, S, S, T, we have to already calculating. So this means we can clearly this I just said that I had to forget this, can x, y, z can be written as a, this is x times, so this is x plus 3 times y plus 3 times z, and then you have a minus x, and then you have a minus 5y, and then you have a x, and then you have a minus 2z. So this is the general formula for T or ST. Then you can just similar fashion where I calculate the RS, you can calculate the ST, and then RS already we have to calculating, then you have to apply the T here, and then you have to find the what is the range of this. That means you just find the kernel of this kernel of this set, and if the kernel is equal to 0, then we can say dimension whatever the element in the kernel of this is the basis, a linear independent set. Similar fashion we can find the range. Range is always of the form of this form, and then we take all these three vectors are linearly independent. So I just say that we can just say that this complete the solution of this problem. Okay, let's now move to the next problem, where this is said that we have a two linear transformation. We have a t from u to v and s from v to w. Then t is onto. So we can say that if t is onto, so we have to find the rank of st is the same as the rank of s. And if s is a 1 1, the rank of st is the same as the rank of a t. So we have two conditions are there. If we have a t is onto, so we have to show that the rank of st is equal to same as the rank of s. So for rank of st, first we find the what is the image of st, and then also we find the image of s, and then we have to take into this form. So first we try to show that the range of the method of solving this, we have, if we show that the I just say the range of this range of st is the same as the range of s, then we use the dimension theorem. Dimension of this means we can say the dimension of a range of st. If these two are equal, then we can say that dimension of r s also equal, and if dimension of r s, this is nothing but is equal to, we can say that rank of r s rank of st is the same as a rank of s. So proving method is simply is this: we have to show that the range of st is the same as a range of a s. Okay, let's try it. Because t is onto and we take a s is a, we have a map from v to w, t from u to v. I just note down. So t from, you have a u to v, and we have s from v to w, then is well defined. Now t is onto, we have a given. So we take a w is any element of a range of a st. That means w, because you have a v belongs to this, then s of v is always the element of a w, and here u is the element of a u, because t is onto, then there exists a element of a v belongs to v, such that t of u is equal to v by the ontoness. So we have to choose any arbitrary element in the range of a s. Then there exists a v belongs to the v. By the this definition, we can say that s of v can be written in the form of a w. And now we have a given t is onto. So we have also given since t is onto. There exists a u, because you know that t is from u to v, s from v to w. So this means there exists a u such that t of u is equal to 0. Okay, now we have to try to calculate the, because we have to show that this w is the element of a range of a st. So we can say if w is the range of a st, means we can say that s of t, because the composition map is defined like this, you have a, we try to show that st. So st means we have to just take a u to v and v to w. This is t, this is s. So this is st. So st is what? St is nothing but we have to calculate the s of t over the u, because st is mapped from this linear st is mapped from u to w. So we can say that any arbitrary element of a u, if we show that this st is nothing but is equal to w, then this w is the element of a range of st. So we take as image of a composition. By the definition of a composition map, this can be written as s of a t of u. And now because we use the t of u is equal to v, so this s of u have a v, and now s of v you have a what? S of v is you have a w. This implies that we can say that s of t of u can be written as any element, this w as the element of a w, because we choose this element of a w. So this implies that this w is the element of a range of st, and why we have to choosing the w is the element of a range of s. So this implies that range of s is subset of range of st. So first way is we have to prove that, we have to assuming this is equation number 1 for the moment. So I just take into this form, I just said that this is equal to 1 in this form. Okay, now next we have to show that this converse part. So we take as a w is the element of a range of a st, then we have to show that this w is also the element of a range of a s. Okay, so now we have to take w is the element of a range of st, then there exists a u such that s of t of a u is equal to w. So we can write a w is equal to, you have s t of a u, and then by the composition map we can say that S of T of U. And now because T from U to V is a onto map, and if onto map, then U belongs to U, there exists a V belongs to V, such that you have a T of U is equal to V. So, this we can say that S of V, and then we can say that S is a map from you have a V to W. Then clearly if we have a V is the element of a V, and then we have an image S of V types element to W. This implies that we can say that W is the element of V. S of V can be written in the form of a W. So, we can say that W is the element of a range of a S, and then W is we have to assuming the range of a ST. So, this implies that we can say that by this we can say that the set theoretic property range of a ST is containing range of a S, and now this can be shown that the second part we can say this is equal to 2, and also we already show that the range of S containing in the range of S of T. And by these two, this is the first, by these two combining this we can say that range of a S is the same as a range of a ST. Now take a dimension of a both, the dimension of a range of a S is the same as a dimension of the range of a ST, and then this is nothing but is equal to this is a rank of S is the same as a rank of ST. This is complete the first part of the this example. We have to just say this we show that using the ontoness of a T, and then this is equal to SV is equal to W. So, we can say that W is this, and then clearly by this we have to show that this complete. Okay, now next part we show that is a we have a S is 1 1, and then we have to show that S is 1 1, then rank of ST is equal to this. Now, you show that 1 1 means we have to just show that we try to first in the two parts. First we show that the null space of this and the kernel of we can show that kernel of ST is the same as a kernel of T. So, we proving this. So, we take a because of U is the any element of we choose as a kernel of we have a ST, because map is ST is always is a map from U to W. So, we took a kernel of a ST is equal to this, and now this implies that if U is the element of a kernel of ST, we can say that ST over U is equal to 0. Now, by using the composition mass property, S of T of U is equal to 0, and now you just say that S of T of U is equal to 0. This can be written in the form of a S of T of U is equal to S of 0, because S of this 0 map is equal to 0. Now, S is you have a giving 1 1. So, you know that S is 1 1 means S of U is equal to S of V, implies that U is equal to V. So, this implies that we can say that this implies that T of U is equal to 0 by the 1 1ness of a S, and if T of U is equal to 0 means U is the element of kernel of ST. If this is the element of a kernel of ST, this implies that we can say that we at assuming the U is the element of a kernel of a ST, and we show that U is the element of a kernel of kernel of a T. So, this implies that we can say that kernel of ST is containing that kernel of a T. Now, similar fashion we can use if U is the element of, because T is mapped from U to V. So, U is the element of a kernel of a T, then we show that this implies that T of U is equal to 0, and now if T of U is equal to 0 of V, now we can say that S times of a T of U is equal to S of 0 of a V, and S is mapped from you have a V to W. So, S of 0 of a V is the same as a 0 of a W. So, this means we can say that S of T of U is equal to 0 of a W, and this implies that U is the element of a kernel of ST, and then we have to assuming that U is the element of a kernel of a T. Now, we show that U is the element of a kernel of a ST. This implies that we can say that kernel of T is containing in the form of a kernel of as t. This by this and this 2 we can say that kernel of a t is the same as a kernel of S t, and we also say that dimension of kernel of a t is the same as a dimension of kernel of S t. Okay, now this way we can just say that this is satisfy this condition up to here. By these two conditions we can say that into this form, and then by the rank nullity theorem we can say that dimension of a u can be written as a dimension of a this thing, and also we can say that dimension of a u can be written as a dimension of range of S t plus dimension of range of this is kernel of t, and then because these two is also dimension equal, this is also dimension equal, this we can say that this is the same as a dimension of a range of a t plus dimension of a kernel of a t is the same as dimension of a range of a S t plus dimension of a kernel of a t. Now we already show that from here we show that dimension of a kernel of a t is the same as a dimension of a kernel of a S t. So this means these two are cancel out. So ultimately what we have to show, the dimension of range of a t is the same as a dimension of a range of S t, and if range of this is, we can say that rank of t is the same as a rank of a S t. Okay, now this complete the this complete solution of this problem. We just say that into this form. So range of S t is equal to, we have to prove into this form. Okay, so now just set one more problem I just and then stop. This is suppose T from V to V be a linear operator of a finite dimensional vector space, then range of a T and kernel of a T is equal to 0 if and only if Tx square is equal to implies that Tx is equal to 0 for or arbitrary. So we take a if and only if condition is there, if this is equal to 0 then we have a T, if Tx square 0 then Tx is equal to 0. If this condition is hold, we can say that range and RT intersection kernel of a T is also is equal to 0. So starting from this, assuming that this range of a T is equal to 0, we choose any arbitrary element x belongs to V, satisfy Tx is equal to 0. Now we use the composition map. We can t square x we can write into this form like this way. 0 can be written as a t square x. This can be written as a by the composition property t of x. And now we have to just say that t of tx is equal to 0, and then this implies that we can say that this means t of x is the element of a kernel of t. And now we just say that t of x is the element of a kernel of a t, and also because you know that t from V to V, then if we have a x is the element of a V, then Tx is the same as a range of a this. This implies that Tx is also the element of a range of a t, and now Tx is the element of a kernel of a t, and Tx is also the element of a range of a t. This implies that we can say that Tx is the element of a range of a t intersection kernel of a t, but this thing is equal to 0. So this implies that we can say that Tx is equal to 0. So this completes the first part. If range of a t intersection kernel of a t is equal to 0 and t square x is equal to 0 implies that Tx is equal to 0. So this is we have to prove this first part. Now next part we have a condition t2x is equal to 0 implies that Tx is equal to 0. And now we show that we take any arbitrary element V in the element of a range of a t and kernel of a t. So this means V is the element of a RT and V is the element of a kernel of a t. If V is the element of a RT, this means T of this is the element of a, and now this is kernel of a t means you have a T of a V is equal to 0. And also we have to just say that this is we can say that this range of a t is the element of a this. So V is the element of a RT, and then T of V is equal to some y. Y is the element of a V, and by this property we can say that T of V is equal to we have a 0. And now therefore we can say write operate the t. So we just write as a t square y. then t square y can be written as a t times of a t of y, and t of y is equal to, you have a v, and then this is t of v is equal to, we have a 0. So by this we using these two conditions. So t square y is equal to 0, but t of y square y is equal to 0, we have to getting is equal to this is 0 means y is equal to 0. So this means y is equal to 0 means v is equal to t of y is equal to 0. So this means t of, because t of y is equal to 0, we have a given condition t of t square y is equal to 0 means t of y is 0. So we have a, this implies this is 0 means t of y 0, t of y is what, v is equal to 0, and we have to choosing from where, v is a choose the element of a rank of a t and intersection kernel of a t. So that means we shall show that rank of t intersection kernel of a t is equal to 0. So this complete the proof of this problem also. So now I just say that I just complete this problems. I just leave one problem for you as a home assignment. Where T is a linear map of on R3, define T E1 E3, E2 is equal to E1, E3 is equal to E2. Then you have to prove that T square is equal to T inverse. So this is your home assignment. Now I just complete the portion of this composition of a linear transformation. Now I have to stop today's lecture here, and then next class we start the matrix of a linear transformation. So how we represent a matrix as a linear transformation. So we have to in the next class we discuss about the how to define a matrix in a linear transformation, and then further how to, if a matrix is given, how to we construct as a linear transformation in the both the way. And then if a matrix transform, every matrix is in the form of a linear transformation, then how to find the rank, kernel or nullity of such a matrix, we discuss into the next few lectures. So thank you very much for this today.